we need to represent the displacement involved. We need to represent the displacement involved. So for axial deformations, if we have a bar, its cross section can be, it can be changing, not necessarily constant. Okay, the E also can change. So for bar problems, the axial deformation, we have to represent that. Similar later for bending, we need to have a variable representing that deformation. So it's the same thing as what we have covered under theory of elasticity. So the axial deformation here is represented as U, which is the axial deformation. And this is a function of X, okay? This is a function of X. Then the corresponding strain, these are the variables that we have, will be du dx. Okay? Will be du dx. So the displacement is u as a function of x. So the strain is du dx. And of course, we have a stress. Right. So this is the displacement, happen in the case of axially loaded bar, u. Okay? And it's a function of x only. And the corresponding strain is du dx. So now we want to make use of this to substitute into here. Then take note, this is linear elastic materials. So the strain is related to the stress through the stress-strain relations. Okay? So we have stress, okay, which for our linear elastic materials, it will be E epsilon x, okay, and this will be E du dx. Okay. So it is important for you to take note that we are talking about linear elastic material now because we introduced this relationship. Okay, of course, this is already for linear elastic material. So what we do next is, class, we want to get the strain energy this. So in order to get this strain energy, we need to know this. And this one for linear elastic materials, for the case of axially loaded bar, is given by these equations. And here, we want to express everything in terms of U only. So stress is given by these equations, and strain is given by these equations. So we substitute there. We substitute the VP, this one, which is that here, this one in terms of U. We want to express the strain energy, everything's in terms of displacement. Okay. So that is the process that we want to go through. So if we go through that, then our strain energy that we need in order to derive, in order to get the equation for strain energy will be given as, we need to make use of that equations. So we make use of this equation, okay? So we will put it here, integration over the volume first, integration over the volume, this one. And consider this and this into here. So I have half E, okay, du dx appear twice. Okay. This is d volume. Yeah? At this stage is still d volume. Okay. So now we have to look at what is the meaning of d volume. So d volume here, we integrate over the volume because strain energy is integration over the volume. You add up all the strain energy density over the whole volume. So for a bar problems, okay, then at the particular location X from the origin that we have chosen, let's say the cross-sectional area here is A. Okay. The cross-sectional area is A. So now, if we move to the next one, a very small distance, say this is the x. Okay. This is the x here. So we can represent the small volume of this bar, the d volume, a small volume of this bar can be represented as A multiplied with dx. So cross-sectional area multiplied with this small distance give you a small volume here. So now if we have this d volume here, we substitute there, okay, and then we integrate. A can be changed. It can change. A can change along x. So A is a function of x. So now if we take this into consideration, if we substitute there, so we are going to get our UPS finally integrations 0 to L now. From 0 to L now, half AE, because A comes from D volume, and then du dx squared dx. Okay. So in this way, we get the strain energy equations, these integrations, okay, for the case of bar, which is cross-sectional area change. So this A can be constant, A can be changing, E can be constant, E also can change. So if A is constant, you can take out the A doing integration. If A is not constant, then you have to consider, you have to know what is the function of A, okay? Now later, when we want to apply this, when we see the application of this, we make assumption of this. In our later approach of solving problems, we want to solve for U. We don't know what is U, but we make assumptions about the solutions. Maybe sine, cosine, maybe polynomial. So we make assumptions. Then when we make assumptions about what is U here, then we can differentiate U. Then we can get the strain energy. So that is why we need to know the strain energy for this first case, axial deformations. So class, this is the equations that you need to remember. If there is a bar subjected to axial force, then it has axial deformations, then you need to use these equations. Half AE du dx square dx. U is the displacement. A is the cross-sectional area, which will change, and E is elastic modulus, which also can change. Okay? So that is the first equation that we want to derive. Okay? So we start from definition of strain energy, which is this, and we apply this for the case of linear elastic materials, and we go through this process, and finally we get to these equations. Okay, and this process is explained in detail in the notes. Okay, I just summarize the process. You can refer to the notes again, and also I have recorded this. I think if I try to find a way to share later with you if you want to refer again. So that is get the first equation. Now we want to go to the second equation, which is bending. Okay? This is the first equation that we get, and this equation is given in the notes as equations 5.11. I refer this to the notes. This is 5.11 in the notes that I have shared with you on the e-learn. Next, we want to go to next set of equation, which is for bending. Okay. So before that, any questions? Any questions from anyone on this derivation process? can go through again, okay, on this set of notes, which is. So the next one is on bending now. Okay, we want to go to bending. Any questions? Now for bending, okay, for bending, we still start with the same equations. We start with the same equations for bending. And for bending, we are making use of a certain theory, okay, which is in beam, we have certain theory of beam that researchers has developed, okay, and it has certain assumptions about how the beam deforms. So we will make use of one of the simplest theory for the beam. I have to erase this, okay? Now, by the way, I have put up a kind of link on the e-learn. I don't know any one of you aware of that. I would like you to tell me what do you think about the lectures so far. So this is week number 6, because particularly the way I conduct the lectures and the materials that I share with you, is there anything that you feel like improvement should be done? So please go to EAS661, the e-learn. There you answer some questions there so that hopefully I can still improve later on when I take over EAS663, okay? So that's a kind of survey, okay, just for me to know whether you are satisfied or maybe you have some suggestions. Maybe put some coffee here or whatever suggestions that you might have on the teaching, the way teaching has been conducted so far. Okay, this is on EAS661, the e-learn page. I don't know any one of you are aware of this. Okay, because we want to hear from you whether you are satisfied or not satisfied. So every time teach, we are very hungry. Please give us some time to eat. Please give us some time to drink. Please, we need some time to exercise. Okay, or aircon is too cold, or aircon is too hot. Okay, yeah, or the voice is not clear enough, or okay, all kind of things related to teaching. Okay. Now, next we want to go to bending. Okay, bending. So the starting equation is still this. So you see, this is a very useful general equations, and again, the strain energy density, these small things here, is also the same, which is in general it is like this, yeah. But for linear elastic, again, for the beam, we look at linear elastic beam. So we are still using linear elastic. So this one is this. This is for linear elastic. So it's the same. Okay, until now for the case of bar and beam. Okay. So we need to integrate. We need to find this for the case of beam, we need to integrate. But for the case of beam, which is one of the things which is different from the case of bar, is this strain energy density is not constant over the cross sections because the stress changes. Because the stress changes, but for axial deformation, the strain energy density is constant over the cross sections because the stress and the strain is constant over the cross sections. Okay. This is one of the things which is differentiate, because for bar problem, okay, so over the cross section of the bar, the stress is constant. The stress and strain constant. That's why the strain energy is constant over the whole cross sections. So that makes integration easier. But for beam problem, if you have a cross section over the beam, okay, the stress changes and the strain changes over the cross section. So the stress and also the strain is not constant. This is not constant. So when the stress and strain is not constant, so if you find the strain density, strain energy density half sigma x epsilon x, so at different point they are different. They are different point, they are different, and we need to integrate that over the whole volume to find the strain energy for bar in bending. So it is not constant. Okay. So for the case of bar, you know that if I have a bar here and you cut through this cross section, so over the cross sections, the stress and strain are constant. Okay, this is the stress like this, constant. This is the assumption that we make for bar. But for beam, this is for revisions. Okay, for the case of beam, if you have a beam supported here, and if the bend, and if you look at the cross section here, then the stress and strain is changing in this way. The stress and strain over the cross sections in the case of beam is linearly changing from neutral axis 0 until the top here. Here may be compression maximum, tension maximum at the bottom. So it is not constant for the case of beam. That's why the strain energy also not the same at any point. Okay, you have to consider that. So these are the things that I think is a kind of a review, refresh also. What is the characteristics? What are the assumptions that we make? Okay. Now, so these are the things that we need to know. So let me take away this. I need to. So bar constant, beam not constant, changing in this way. Later for twisting, later when we go for twisting, then also the strain energy will not be constant because twisting causes shear, shear stress. The shear stress is not constant over the cross sections. Okay. So now I would like to go to how to get this for the case of beam bending, and then substitute here integrations in order to get the strain energy for beam. Okay. Now, in order to do that, okay, we must be able to relate. Yeah, we must be able to relate this strain. Okay, the strain. So to do that, what we are based on the kind of beam theory that we use. This is Bernoulli-Euler beam theory. Bernoulli. Okay. There's Bernoulli. Okay. Okay, so these are the theory that we use. There are other theory, the Timoshenko beam theory, there are Bernoulli-Euler beam theory. So these are the assumptions that we make use of based on this beam theory. So for this beam theory, I think we can have so when the beam deforms, I think the cross section is going to change in this way. So the top part is in compression, the bottom part is in tension, okay? And then the strain, okay, the strain that we are going to relate to will be related to what happened to this particular length when the beam bends. Okay, this is the sectional shape when the beam is subjected to bending under Bernoulli-Euler beam theory. So before that, the beam shape is rectangular, for example. This is neutral axis, the length remains the same. So under bending, so this is what happened. The top part in compressions, so all the length becomes shorter. So the bottom part, all bottom part is in tension. All the length here, if we measure this length here, all become longer. All the length here above neutral axis, because of the top part of the neutral axis is in compression, the bottom part is in tension. So all the length of this thing becomes shorter above neutral axis, and all this length here below neutral axis become longer. So it is a kind of extension that happens along the sections, but the degree of extension are different because this is bending, not like axial deformations. So this is just to try to relate to how we calculate this strain. So we calculate the strain, we take at a particular distance y from the neutral axis. Okay. We take at a particular distance y from the neutral axis, and here this is the same location y. Okay. Same location y, and if we extend here this and this, we extend these two lines. Okay. So this is going to make an angle, let's say d theta. And in bending, we have what we call the curvature. We have what we call the curvature, and that curvature is represented by a radius. Okay, a radius. So we represent this is radius, okay? Radius of curvature at that particular point. Okay, so this radius will change depending on the loading that we have on the beam. So this, imagine this is a neutral axis. Okay. So now the length before and the length after, the difference between them divided by original length give us the strain of this particular line. So this is related to this line getting longer or getting shorter. So we go back to the definition of axial strain. So here, we want to get this term now here. So epsilon x at this point here, okay? Now epsilon x is changing now. Epsilon x at this point here is the length of this after bending minus the length before bending over the length before bending. So this one rho minus y, which is this distance here, multiplied with d theta to give you this length. Then minus, minus original length. Original length is this, which is rho d theta divided by original length So this gives us the strain. This is an axial strain at this point. So when y changes, then the strain changing. So when y is 0, you get strain 0. When y is equal to 0, which is here, you get strain 0, meaning the neutral axis, there's no stretching. This is the assumption that we make for beam theory. At neutral axis, there is no stretching. So the stress is 0. So here, if we simplify this becomes minus y over rho. Okay. Right. So this is the expression for axial strain at this particular location y from neutral axis. So this is this one. So now we want to relate this to, normally in beam, we talk about this deflection. We talk about deflection. So we want to relate this to deflection in beam now. In beam, we talk about deflection. Yeah? So deflection means if I have a beam like this is supported here. I use this example, and under loading, the beam will deform. The beam will deform, meaning that it's not a very So I represent only using the neutral axis, okay? The beam will deform. The beam will deform, and the beam, we have this coordinate system for the beam, which is, this is x axis of the beam, and this is y, okay? So this is normally the way we use the coordinate system for beam problems. So x is the axis, y is the deflections, the deflection. So under certain loading, okay, under particular loading, for example, a loading like this, then the beam will bend. I represent only using neutral axis, so the neutral axis will become like this. Okay. Okay. We represent this using a function what we call the V. Okay, V, which is a deflection of the beam, so it represents this. V is this. Okay. So that is the displacement that we use for the case of bending of beam. Just now for the case of bar, we have U, axial displacement, but here we have transverse displacement now, which is V, which is in the direction of Y. So when we want to get the strain energy, we want to get the strain energy in terms of displacement. Same thing like what we have done for the case of bar. So now we want to relate this rho, we want to relate this radius of curvature to V. We want to relate the radius of curvature to V. Okay. So now I write down the strain is equal to negative y over rho. This is the radius of curvature. Radius of curvature. Okay. Now, I write down this as minus y plus 1 over rho. Okay. So this 1 over rho, normally we call them a name called curvature. So strain is related to curvature by that equation in beam. Minus y multiplied with curvature. So y is the distance from neutral axis. Curvature is the same for all the cross sections, but y changes. When y changes, your strain changes. Again, y is 0, curvature, the strain 0, which is here. So now we need a relationship between curvature and this. So for that, we restrict ourselves to small displacement. Our problem is linear elastic small displacement problem. So for small displacement problem, okay, the curvature can be approximate using okay, I have, let me go up here. Okay? So curvature is approximately equal to, this is for small deflection. Which is the normal problem that we look at, the linear elastic small deflection problem. Small deflection problem, the curvature is approximately equal to this. So that's why we can write our strain. We can write down the strain, our strain here to be minus y d2v dx2 here. So class, yeah, with this substitution of the curvature, then we get d2v dx2. So now we get the strain in terms of this displacement representing the bending problem now. Okay. So this is what we want. We want to get the strain negative y d2v dx2. This d2v means you differentiate 2 times. Yeah? Differentiate 2 times respect to x. The function of this, you get approximate representation for the curvature. And that is for the strain. Okay. So now we want to put this here. And we want to use the stress-strain relations. Then get this one we put inside here. Then we integrate, then you get the equation for strain energy for bending. So that is the things that we want to do. Okay. And to do that, let me take away this one. Okay, this is the Bernoulli-Euler beam theory. So now, strain energy is half sigma x epsilon x, which is not constant over the cross section. Then this one will become half E epsilon x epsilon x. Now epsilon x is that particular function, negative y d2v dx2. So you are going to get half E, y appear 2 times the square, so become y square d2v dx2 square. So this is the strain energy density equations expressed in terms of the displacement of a beam, which is this displacement V here. So this is strain energy density. So next, integrate. Next, we have to integrate this. So integrate now, we have to substitute this half E y square d2v dx2 square. And the d volume here, we have to change it to dA dx. Just now, we directly using a dx because everything is constant over the a. So, but now, because this is changing over the cross section, so we have to use this to represent the volume, okay, dA dx. So now finally, if we try to integrate that, and this is constant over the cross sections. Okay, this curvature also constant over the cross section. Curvature does not change over the cross section, means only the thing changes is y. Okay, so that means UP is equal to, you can integrate it, take it out. This one is half E square, and then integrate, multiply with y square dA dx. This is, the rest of this is not a function of, it does not change over the cross sections. Only y square is changing over the cross section, so that's why only y square remains when we want to integrate with under dA. So this is the classical definition of moment of inertia. This is the definition of moment of inertia. Moment of inertia of a section, okay, I, which is, this is moment of inertia, okay. So finally, we substitute that, then you get this is integration 0 to L half EI, differentiate V twice, square, then integrate from 0 to L, the length of the beam. That gives you the strain energy for bending of a beam. And this is question 5.19. Okay. In the note, this is equation 5.19. So you can find the explanation in more detail as what I explained just now, how to get that. So we have derived these two